Before we dive in deep to the physics of semiconductors and semiconducting materials, I'll stop here and describe some of the devices that is motivating that physics, because it's a lot easier to appreciate why you want to know these things about the carrier concentrations, the density of states, the Fermi energies, and everything else that comes into the physics if you know a little bit about how that's used in the design of a device. So I'll describe 3 device categories, starting with junction devices. Junctions dominate semiconducting device characteristics, especially in integrated circuits where we're dealing with transistors. They're filled with junctions. If you don't have junctions, then you're not going to have nonlinear semiconductor devices. A p-n junction is made from 2 types of semiconductor materials, a p-type hole-doped material and an n-type or electron-doped material. The prototype we'll illustrate with here is a single ribbon of semiconductor, all one material, perhaps silicon, and it was formed by diffusing donor dopants and acceptor dopants into it one at a time. First, the right side was masked off and donor dopants were diffused in, and then the left side was masked off and hole dopants were diffused into it. The result is this ribbon that's half n-type and half p-type. A battery is connected to it, with the positive terminal of the battery connected to the p-type side, and the negative terminal of the battery connected to the n-type side. But there's a switch between the battery and the semiconductor. We will first talk about what the carrier concentration across the semiconductor looks like when that switch is open, and it is just a junction that was found sitting there. And we're going to look at how the carrier concentration, the number of carriers per cubic centimeter, varies going from the left to the right, where N is the electron concentration and P is the hole concentration. For now, let's have the switch open so we can answer the question of how are the carriers distributed throughout the semiconductor when there is no bias on it. No current is able to pass through it. That condition is referred to as thermal equilibrium, when current cannot pass through the junction. The left side is full of electrons and the right side is full of holes, and so we can sketch that accordingly in this first graph, which is a carrier concentration versus position along the junction. Let's look at how the carrier concentration varies across, where N is the electrons per cubic centimeter and P is the holes per cubic centimeter. With the switch open, electrons are a high population over on the left side and low population on the right. You see these 2 types of semiconductors are attached, which means that the electrons in the n-type will diffuse into the p-type, because the n-type being full of electrons and the p-type having virtually any electrons will mean that some of these electrons will diffuse over, because when you have a dense population of one particle type in one region and no population in another region, diffusion naturally occurs. The holes will do the same thing, because you have a lot of holes on the right and not many holes on the left, and so holes will diffuse into the n-type region. Now you might wonder, why don't they diffuse more than this? So the n-type region is donor doped. Donor ions are positively charged. An n-type semiconductor all by itself is electrostatically neutral. There are as many free electrons as there are positive donor ions. Charge neutrality will be maintained throughout this semiconductor. So when electrons move from the charge neutral n-type side into the charge neutral p-type side, they encounter not just a bunch of holes, which should be attracting them, they encounter an equal number of negative acceptor ions. And so when one electron moves from the left side to the right side, the right p-type side becomes negatively charged. And when a hole moves from the right p-type side into the left n-type side, the left n-type side becomes positively charged. For now, we will define the junction as the place where the carrier concentrations have gone to half their value deep inside their respective regions. We can look at the energy of the situation. We'll put that in the bottom graph. As you go across the junction from the left side to the right side, the potential energy experienced by electrons and holes is going to change. The electrons have their preferred location where the potential energy is therefore lower, and the holes have their preferred location where their potential energy is therefore lower. In semiconductor physics, we always plot the electron energy, not the hole energy. So the electron energy, as you go across this junction, looks like this. It's lower in the N-type region, and it's higher in the P-type region. For that same reason that I just mentioned, when an electron moves into the P-type, it encounters all of those negative acceptor dopants, and it finds itself being repelled back to the N-type. And so there's a energetically favorable region for electrons. And conversely, your holes are energetically favorable on the right. When an electron is on the right, it's energetically unfavorable. It is in a more negative electric field, meaning that the potential energy of the electrons, which equals minus Q times the potential, goes up. Just remember that when charge is in a region of the same charge, it goes up. And so when that electron encounters acceptor dopants, it wants to go back home. So the potential energy of an electron goes up as it diffuses into the p-type region, and that's reflected in this graph of the electron's energy as it goes across the junction. It's lower on the N side and it's higher on the P side. And so the electron's energy goes up as it diffuses into the p-type region, and that's reflected in the energy level diagram of the conduction electrons as the energy goes up and amount delta E. So the electrons go into the p-type because there's a low population of electrons over there, and that's what diffusion is, going to where their population is low. But when they get there, they find themselves to be electrostatically unwelcome, and so they roll back downhill. So that's the conduction band edge. All free electrons have an energy that is higher than this energy called E sub c. Then there's the valence band edge. All bound electrons that are stuck in atoms have an energy that is below this level. The separation between the conduction band edge and the valence band edge is the energy gap. And it's the same throughout because doping doesn't change the energy gap. So E sub g, like 1.12 electron volts for silicon, is the same everywhere across the N and P types. Okay, so if I took my electron tweezers and dragged an electron from the left side over to the right side, I'll be dragging it up a hill of height delta E, the built-in energy, which is best referred to actually in voltage. So it's Q, 1.6 times 10 minus 19 coulombs, times the built-in potential, P sub Bi. We'll encounter this quantity, built-in potential, a lot over the next quite a few chapters. It's simply the difference in the conduction band edge on the P side minus the conduction band edge on the N side. Phi sub Bi, the built-in potential, is what you would actually measure with a laboratory instrument with contacts placed on either side of the junction. If you replace the battery with a voltmeter, you would read Phi sub Bi. So the electron does have to climb a potential hill to get from the N side to the P side, and that's a big deterrent, but you also have the diffusion force pushing it over there. And so there's a trade-off between the electrostatic repulsion that it encounters when it gets there and the fact that the concentration gradient drops off, attracting therefore the electrons over to there. I want to point out one more energy in this diagram, and that's this horizontal dashed line labeled E sub F. F is for Fermi. Doesn't show here, so I'll just spell it Fermi, is the Fermi energy. It's an energy that's characteristic of the semiconductor. When there's no battery connected, as in this case, it's a horizontal line. When we close a switch and apply a potential difference across the junction, the shape of that Fermi energy will change. But for now, it's just a horizontal line. The Fermi energy is in the gap, and it's always closer to the conduction band edge in an N-type semiconductor, and it's always closer to the valence band edge in a P-type semiconductor. And so you can think of that as an explanation also for why these bands have to bend up, because that condition has to be met with the Fermi energy as a horizontal line. It has to be closer to the valence band on the right and the conduction band on the left. So this is a one-dimensional energy band diagram following the energy as you proceed in one dimension from the left side to the right side. I do want to mention one thing about this energy gap. So it's the same everywhere throughout the junction, provided the junction is one base material. So provided it's fabricated as I described. A piece of, say, silicon that's been N-doped on the left and P-doped on the right. Quite frequently, junctions are made from two different base semiconductor materials, in which case they're called heterojunctions. And that's done specifically to get a different band gap on the left and the right. So it may be silicon on one side and some alloy on the right side. So that's with the switch open. No current passes through the junction. And we're in a condition called thermal equilibrium. So think of those as synonymous. No current passing through a junction and thermal equilibrium. When you're in thermal equilibrium, there is no current passing through. The Fermi energy is a horizontal line. It will be different when current's allowed to flow. We're not going to address that until later. So let's go ahead and close the switch. When we close the switch, now we've placed a positive potential on the right end on the P-type side and a negative potential on the left end on the N-type side. So the N-type is filled with electrons, but we've put negative potential over here. Those electrons are chased to the right. They feel less of a problem with heading into the P-type because they really don't like it over here anymore. So they have less of a potential hill to climb. That built-in potential is no longer the barrier it once was. The height of the potential hill has become less. It used to be Q times the built-in potential, but now we have to deduct the voltage of this battery from the built-in potential to get the new voltage difference between these two sides. It subtracts it to the opposite. So now there's a shorter hill and less of a voltage drop across the junction. Electrons have a much easier time getting across. This bias condition is referred to as forward bias, where you put the positive voltage on the P side and the negative potential is in contact with the N side, and current goes through much more readily. I drew the Fermi energy as still horizontal. That's not really right. If you have a significant amount of current going through the junction, it will change shape, and that will be a subject that we have to consider later. We will consider extensively later. So for now, we're not going to focus on what the Fermi energy looks like when we have current going through. The gap doesn't change. The battery has no ability to change band gap. So it's the same. If this is silicon base material, it's the same 1.12 electron volts all the way across. Now if we vary the voltage, starting at 0 for the origin and increasing it as we go to the right, we can measure the current and generate a current voltage characteristic. We can flip the battery around, put the positive terminal on the left and the negative terminal of the battery on the right, and be to the left of the origin, have negative voltage. So those two conditions are referred to as forward biased when you have the positive terminal on the P-type, or reverse biased when you have the positive terminal on the N-type. And if you measure current versus voltage, you get this exponential behavior described by the Shockley Diode model. In the Shockley Diode model, you have QV, Q, the charge of the electron, 1.6 times 10 minus 19 coulombs, V, the applied voltage, K is Boltzmann's constant, T is temperature in Kelvin. I0 is the reverse bias current. When the voltage becomes negative, so if you flip the battery around and you have a large negative voltage, this term very quickly becomes negligible. and you just have I equals minus I0 for large negative voltages, and it levels off. So that's why I sub 0 is called the reverse bias current. And then there's the ideality factor, eta. Oftentimes eta is just left at 1, meaning ideal. But in a real PN junction, you have a phenomenon at the junction going on called electron-hole recombination, which alters the behavior of the diode, and this ideality factor is meant to describe that empirically. For a lot of integrated circuit devices, we can go ahead and take eta to be equal to 1, especially since we're focused primarily on the field effect in integrated circuits rather than the PN junctions. Real data indicates a much stronger dependence on voltage for a germanium-based diode than a silicon-based diode. A germanium-based diode will pass a lot more current as well. They both follow the Shockley Diode equation, but the reverse bias current for a germanium diode is much larger, 1/10 of a milliamp, compared to 1/10 of a nanoamp perhaps for a silicon-based diode. And the consequence of a larger reverse bias current is that you also have a larger forward biased current because of just the structure of the equation. So 2 salient points to remember about PN junction devices is one, that there is a built-in potential, phi sub bi. It's a consequence actually of the doping level, and it's going to keep coming back to us, so we'll have to get comfortable with the idea that when you connect a P and an N-type semiconductor together, there's a potential hill that carriers need to climb to cross over to the other side. The second salient point is that the band gap is a constant throughout a junction fabricated from the same piece of semiconductor, and it does not vary with either doping or with bias voltage. Now I'll speak briefly about 2 other device categories, the field effect devices and the optoelectronic devices. Those are the 3 device types we'll cover in this course. The field effect is the really fundamental basis of the transistors that are used in integrated circuits. Imagine a p-type semiconductor, and I have an electrode that faces it, and there's an air gap between them. The electrode is held at a voltage V. The p-type semiconductor is grounded. The voltage is positive. So as I turn up that voltage, start at 0 and then turn it up higher and higher, I have this capacitor formed from it where I have a positive charge on this electrode plate. That chases the holes out of the p-type. As I slowly raise this voltage, holes begin to exit the p-type, but also as I slowly raise this voltage, electrons come from ground into the p-type. And they're very strongly attracted to that electrode. They just can't get to it because of the air gap. So what they do is they form a layer at the top of the semiconductor slab. And so you have this layer of electrons in what is otherwise a p-type semiconductor. So you have this top region of the p-type semiconductor that has been converted into an n-type, and it's called the n-type channel. The voltage on that electrode, where the n-type channel begins to establish itself, is called the threshold voltage. And once you exceed that voltage, we say that the semiconductor is in inversion, because now there is a layer on the top of the semiconductor that has inverted to the other type. This is the essence of the electric field effect. The transistors that we're going to focus on in this course, field effect transistors, operate on the principle of this effect. This sort of capacitor and PN junctions are integrated together into a single device called a field effect transistor. And we're going to be studying that in quite a bit of detail. The device type that dominates the design of integrated circuits is in fact the Mosfet, the metal oxide semiconductor field effect transistor. This field effect capacitor is the beginning, the building block for all of that. When we finish PN junctions, we will do an entire unit on optoelectronics, LEDs and LED lasers. Light-emitting diodes are based on a PN junction. When you forward bias a PN junction by putting the positive external voltage on the P side and the negative external potential on the N side, the bands become less bent. The conduction band edge moves up in the n-type, and there's less of a potential hill for electrons to climb to get over to the p side, so they do. And they go over to the p side. When they're over there, they find a hole, and what is a hole except an electron vacancy? So an electron sees a vacancy down there in the valence band where the energy is much lower, so that's preferable, so it goes there. And in the process of going down to the vacancy, it emits a photon. Electron hole annihilation produces a photon, and you might say, what's the chances of that? Because the holes will also diffuse over into the n-type side, and you might not have sufficient electrons and holes in the same region to get a lot of light, and that would actually be very true. LEDs depend on a fact that is going to become important for us soon, that electrons are much more mobile than holes. They both move, but electrons move more readily, and so the p-type side can fill up with electrons more easily than the n-type side. What you end up having then is in this region near the junction on the p-type side, you have a high population of both electrons and holes, and they recombine in that small region, creating a very bright light. So that's a very brief overview to how an LED works. We will go in much more detail later when we have finished up with PN junctions, and we'll look at the physics of how that photon is generated and how that affects the design of an LED, and as well as we'll look at what the materials issues are in making efficient light emitting diodes. So those are the three device types: the PN junction, the field effect devices, and the optoelectronic devices, the three categories that we're going to spend time on this semester. Next, we'll start talking about the physics of semiconductors, what the carrier concentrations are, why they are what they are, how they can be controlled, how doping can affect the carrier concentration, and what that does to the performance of the semiconductor. That's all coming up next.